I'm presenting iterative refinement with Fourier-Based Restormer for accelerated MRI reconstruction, which is a joint work from NVIDIA, Rice University, and Technical University of Munich. The focus of our work is on accelerated MRI reconstruction, which is a compressed sensing task. The goal is to recover a high-quality ground truth image from a set of undersampled measurements, and these undersampled measurements are obtained by applying a known forward process to the unknown ground truth image X. Now, this forward process is just a combination of a mask, which is just an undersampling mask, and the Fourier transform. So these measurements that we have access to are actually recorded in the frequency domain. The current state of the field is that state-of-the-art deep learning-based models have advanced the field significantly. They outperform traditional sparsity-based methods, and they achieve a reconstruction accuracy high enough such that the reconstructed image is very similar to the ground truth image. In this work, we propose a new state-of-the-art, which quantitatively achieves on-par performance with the current state-of-the-art models. And qualitatively, it is capable of recovering more nuances and small features in the image compared to the current state-of-the-art. There are two major components in our work. We are proposing a deep learning-based model, and it's also combined with iterative refinement. And these two are the two critical elements of our work. Now, let me walk you through the rationale and the intuition behind the current state-of-the-art models. These models have an optimization explanation. So they are rooted in optimization and they are combined with deep learning. Suppose we have access to these undersampled measurements Y, which is our undersampled k-space. Traditionally speaking, one would run an optimization algorithm on this least squares problem to find potential solution to the problem. Now, after a while, people started to add a regularization term to just limit the space of potential solutions by searching for solutions with desired characteristics. The most famous one is probably sparsity-based methods, which assumes or imposes a prior assumption on the data being sparse in some domain. And that domain is defined by psi here. Now, if you take this optimization problem and run gradient descent, then one update or the update rule of gradient descent looks as follows. The first term is obviously obtained from the gradient of the data fidelity term, and the second one is meant to be just the gradient of the regularization function. Now, state-of-the-art models propose to learn this gradient of the regularization function with a neural network. And therefore, the optimization update rule turns into something like this. Now, this was the math behind state-of-the-art models. These are called unrolled neural networks because, as you can see, each update rule here contains a neural network. Now, let's look at the actual block diagram of the neural network to grasp the concept behind unrolled neural networks better. We just saw an update rule containing the neural network here. Now, if you take a few of these update rules and put them in tandem as a sequence, each block in this sequence will be one iterate. And we just saw that each iterate is composed of a result of a data fidelity term and a neural network. So state-of-the-art unrolled networks propose to learn this whole process in an end-to-end manner on a relatively large data set by learning a direct mapping from the undersampled k-space, the low-quality domain, to the ground truth domain. Now, what we propose can be viewed as something also rooted in optimization. Suppose we just take this optimization problem, by solving which we get another set of potential solutions to the problem we saw before. And this time, suppose we use proximal methods to solve this optimization problem. Then one update rule is given by the proximal operator, which can be written as follows. Now, if you look closely, you'll notice that at each step, we are taking the solution found from the previous step and just refine it with this term. So what we propose is to wrap a neural network around the proximal operator here. So we are not unrolling anything. We're just wrapping a neural network around the solution found by the proximal operator at each step. Again, visually speaking, there will be no series of blocks. We just have one neural network that does reconstruction and then one refinement step that is given by the proximal operator. As for the choice of the neural network, we opted to work with a state-of-the-art image recovery model that's called Restormer, which is a unit-style model, but in every block, instead of a regular convolutional block, we have a transformer block. Now, the problem with using such architecture with our iterative refinement paradigm is that transformer-based models are not well scalable to high-resolution medical imaging applications, which is actually the focus of our work, because accelerated MRI datasets are of extremely high resolution. For example, the brain dataset that we work on in this work, each sample has the following dimension. For example, 16 number of coils times 700 times 400 pixels, which causes an extreme overhead in computations when you are training a neural network on this dataset in batches. Now, to make this work, to make this combination of Restormer and iterative refinement work, we decided to explore different approaches to make this model more memory efficient for training. Now, our winning strategy was inspired by several works demonstrating that you can replace attention modules inside a transformer model by non-parametric modules, for example, average pooling. Now, based on that, we simply replaced every attention module in the Restormer model by just a Fourier transform, because what the Fourier transform is effectively doing is also a token mixing mechanism. Now that we managed to make the model more efficient, let's look at some ablations on the effect of modifications we proposed. Now, when we employ iterative refinement, as you can see on the left plot, the reconstruction accuracy monotonically increases as the number of refinement steps also increases. There is going to be a limit on this from two sides. One is that, well, the performance saturates. Another limiting factor is the memory efficiency. Essentially, as you have more number of refinement steps, then the higher your training memory consumption. Now on the right, we see how much memory efficiency is obtained by replacing attention modules with Fourier transform. At no cost in reconstruction accuracy, we gain 2 times better memory efficiency. Now finally, we compared our model against state-of-the-art reconstruction models on the publicly available leaderboard of the fast MRI dataset. And as you can see, our model was ranked second among those models. Just a little bit more details on this setup. Here we considered 8 times accelerated MRI reconstruction for brain samples, because the fast MRI dataset has 2 anatomies, 1 knee and 1 brain. And we specifically worked with the brain dataset because it was of higher resolution, which made it more challenging. To conclude, the outcome of our work is that iterative refinement combined with the state-of-the-art transformer-based models can achieve on-par performance with other state-of-the-art models. And it would be interesting in the future to see how one can leverage iterative refinement to achieve a better performance than regular on-rolled methods. Thanks for your attention.